So we've been working on this project for about 8 years, and we've invented something called a hybrid memory architecture, which essentially, I'm going to talk a little bit about that. But a little bit about myself, I'm an old-time database hand, with a PhD from Wisconsin, worked at IBM, went off to the internet and mobile, and then came back to found this company. And the reason we founded this in 2009 was to provide some kind of technology which was on par with what was available then. I was working at Yahoo then. What was available at Google and Yahoo and all these big internet companies for read-write transactional databases. That's kind of where we started. I'm going to talk, in this talk I'm going to present a bunch of use cases which are kind of extreme use cases in various areas, and how a hybrid memory architecture has helped us solve some of these problems, and what the benefits are. So the first one I will talk about is a use case in fraud prevention for interactive payments. We'll see a little bit more about the fraud infrastructure here, but what happens here is there are a lot of, this is from a real deployment from a company in the Valley actually. So they ended up using a traditional relational database with a cache architecture in front, which is pretty much what everybody does when they want to scale high. Ended up in, they have some kind of budget about half a second to do fraud detection or less. When they needed to scale up about 10x, they ran into too many kind of server sprawl problem. I'll talk a little bit about that and how hybrid memory architecture deals with that. But also, eventually they ended up choosing our architecture because it was built on Flash and so on. And they ended up with a 20 server cluster instead of 150 servers. And I'll talk a little bit more about some of the details here, but I just want to give you a quick overview of some of the big use cases. This one is a retail banking use case. This is quite a different use case. In the fraud use case I just showed you, all the data there is not actually a system of record kind of data. Fraud detection is somewhat of a crapshoot in some sense. You run these algorithms and you want to get better and better and better, but you're not looking for 100%, you're looking for close to 100%, and we could improve it quite a bit. Here, this is actually a system of record running on a database. In this case, the hybrid memory architecture is Aerospike, but this is not a fully consistent database of the CP variety in the CAP theorem. It is actually an AP database. But they actually worked around some of the AP issues to set up a system where they had a backing database, in this case, which is the mainframe DB2. Start of the day, they load data into this architecture here in the front-end system. They run all of their new applications through this. All real-time data feeds go both to DB2 and through the app, they get fed into this database. So during the trading period, all of these apps for finance, and various other trading apps run on this system. So pretty much they have turned off, not turned off, they have pushed to the background their main, what I would call master database, which is still used with all the apps and various other compliance applications that run overnight. Again, once again, here there was a problem with caching. They were running at 150 servers of cache, growing to 1,000. It ended up with having to scale it 6x. They were, that's the 1,000. So I ended up eventually with a 10 to 12 server cluster of Aerospike in this case. Telcos are quite different. Telcos have actually been using real-time databases forever. Either they are typically built homegrown, or there are other databases like timestamp, for example, coherence. They're all being used by telcos for a while. At some point, this particular telco is actually, it's a telco equipment provider, Alcatel-Lucent, and now it's Nokia. What they ended up having to do is to scale their systems higher, and they're not even using Flash here. This is another instance where in-memory I've been talking about hybrid memory, but we also have in-memory is a pretty common and widespread kind of technology, and they use Aerospike in an in-memory setting without Flash in this case. But the main issue here was they needed very predictable latency. All of these use cases, they need predictable latency at very high throughput, and they needed several of these systems running at the edge of their data centers, in dozens of data centers. And the interesting thing about a database is that you can now have in your router access to the same database using maybe C code, where it's very efficient to look at every packet and make decisions, and then a Java application which can be used in configuration in order to basically change your account. And this is something which can happen in real time, and immediately your enforcement on the network layer can continue on the new account kind of information. And that's really important for them to do. Overall, all of these systems I talked about here so far are what are called systems of engagement. They are all about end users coming into the system and or real-time actions being taken. And the important thing is everything has to run with a very low read latency in the presence of very heavy write load. I mean, especially the fraud case, just because a transaction has happened, you're going to have to store a whole bunch of information about it. And you're interested in 100% uptime. And a lot of it is being driven from the behavior of the mobile and internet users. And these are actually seeping back into all of these traditional enterprises. When you use a hypermemory database, you end up using it in the front edge of your system, always front edge of the enterprise. And potentially a lot of it is like algorithmic machine learning algorithms. I did not talk about one particular area where Aerospike has been dominating, which is real-time display advertising, where there's a lot of machine learning algorithms which are going on every kind of impression, every ad that shows up when you go on a mobile device or on your web pages. They're all running through various algorithms, and then people are choosing and bidding on these particular locations and positioning ads there. There's a very interesting market there, but that's where we started, but that's not where I would say most of the world is focused on today. Essentially, the actionable insights I talk about, there are a whole bunch of data warehousing and data analysis that goes on the back end, which feeds into the front edge. The decisions happen here. The algorithms and the various rules are figured out in the the data warehouse, data lake, whatever you want to call it, Hadoop, HBase, Spark, and Aerospike, in this case, the hybrid memory database simply interoperates with all of these things. Just want to give you an example. Why is this whole thing exploding? Right? When I talk about transactions, I'm talking about hundreds of thousands a second, a million a second, low latency, and you might wonder, like if you go into a credit card payment system, they don't do more than a few hundred a second. Right? They don't. It's not like they do a lot of transactions a second. It's just that they do a few hundred. I mean, of course, if you count it for the entire day, it's like probably $1 billion, but or hundreds of millions of dollars. But here, to give you an idea of what's going on, just look at the payment systems, right? Originally, you just have one place where you can enter your credit card. And now you have a zillion places you can. Now you can tap everywhere, right? I mean, if you go in a train in London, you can just tap your credit card and it pays there. You go around, you can provide your credit card on a, you can put it in Apple Pay, I guess, and it goes through Apple Pay. There's a whole bunch of ways in which transactions come in. Now, if the only thing that somebody has to do at the transaction level is to look at who is paying the amount and who is collecting the amount, then the fraud detection becomes very simple and very useless, basically. Because pretty much both the merchant in this case and the user are probably going to be in good standing when this is happening. Right? So, but what you can do is if you have visibility, and this is where the transaction history comes, why you need a database which has got terabytes and terabytes of data, is if you can observe every one of the actors in here, right? There could be more actors than what is there in this picture. There could be a Wi-Fi address, right? It could be the conference Wi-Fi address, it could be the mobile gateway you're using when you're traveling or roaming. It could be, a new phone you just got when you went to a new country and you're using that. All of that can actually be used to track on the, in this case, let's take an example of PayPal or Paytm in India, or PayPal in the rest of the world. What they will have to do is they basically keep transaction histories for each of these actors in the system. Now, if you suddenly find that there's a whole bunch of spurious transactions or some pattern which is emerging, coming from associated with a particular Wi-Fi address in a particular Starbucks in Tokyo, whatever, you can actually immediately put an end to that fraud at that point in time when it's happening. And this is really important, which means essentially what happens is something like this happens, right? There are a few hundred transactions per second, and then you're tracking 1,000 items which you have to go look up for that transaction. Each of those transactions to compute the fraud, the more data you can look up, and with the more transaction history in real time you can carry, you can get a pretty accurate view of what's going on in your network. And then you really have a system which can essentially scale up. So now you're not concerned anymore that people are coming through like a zillion channels to do the payment. And now you make a better user experience for your users. So there's a whole bunch of things. It's not just about fraud in this case. Your user experience is enhanced. Imagine that your card is blocked at the time you're actually buying something, and people are not very happy about that when they have a false positive, as they call it, or false negative, whichever way you want to look at it. Basically, you got something which is actually wrong because you couldn't tell if something was fraud or not at a granular enough level that you end up blocking a whole bunch of valid users, and that's not really a very good idea. So. And then this essentially means that you need a front-edge transactional database which is at the level of a Google or a Facebook in the front edge for an enterprise which is basically doing 500 things per second. This is their business. And that's kind of where all of these requirements start coming from, right? There's one other point I wanted to make, streaming versus a database. Now, in my picture there, I clearly separated out the hybrid memory architecture of something like Aerospike from Spark. Right? Spark runs completely in memory, and it does really, there's all kinds of interesting algorithms there. But there is one interesting thing that you can do with the database, and some of our customers actually were the ones who alerted us to this, is if you, the history case I talked about, if you had, let us say, 1 billion objects you want to track in your database, which is fine, you can track hundreds of billions of objects in a database. And then at runtime, you're interested in information about maybe 100,000 of these users going through the system. That's what you feed into Spark potentially in real time, and it's just computing all of this stuff. Now for these 100,000 items, if you could only join with that 100 billion object database to get the extra history or whatever it is that you're storing in this database, what you have is a much more sophisticated Spark algorithm here, which can not only look at the data which it has gotten recently, but also historical data up to whenever you want to keep it. And that improves by an order of magnitude, maybe several orders of magnitude, what you would call the efficiency and the impact of these algorithms. And then the interesting thing is you can now update for these 100,000 things that you have analyzed, you can update all of this on a very high throughput database. In fact, Cassandra will update quite well too. So you can just update into this big database which scales. And then you have somehow you have combined a very highly scalable read-write system with an Spark-like analysis engine, which is mostly based on streaming and so on. So if which is in memory. So this is something which is worth considering. So having talked to you about a lot of these database kind of the use cases, I can kind of condense it into a few things. We want to have a very heavy transactions per second. Scale should be a lot of terabytes, typically billions of objects. If you're dealing with like 10,000 to 100,000 objects, a million objects, this thing can actually fit in one machine in one node, and you really don't have much of an issue to do scale there. Low latency is very important. When we are talking about sub-millisecond per transaction, we are typically trying to get to 99.9% under 2 milliseconds, 3 milliseconds, that kind of stuff. Okay, the average is very easy to get under 1 millisecond these days. And then reliability, you want to have these systems run up all the time. And this is the really important thing, TCO, right? It is possible, I will show, to build any system. You can take any of the databases which are out there today, and you can build a very highly scalable, highly reliable system. It's a question of how much does it cost you to get there. If it's going to cost you the same amount of effort it costs Google to get there, I don't think most of the enterprises are going to get there anyway. So those are the kinds of things we should think about at scale. So the traditional architecture, kind of hinted on it, has certain significant limitations, right? I mean, essentially what you do is you take it, and I originally worked in relational databases. So what you do is you stick a relational database and put a cache in front of it. And you go like, well, I've solved something. What have you solved? You've solved the latency problem of reads when the database can't deal with it, basically. That's what you've solved. But have you really solved it at scale? And that's what many people find, that there's a lot of issues with caching. When caches fail, you have to reload the entire cache. The whole machine of the cache fails. Then you have to have a distributed cache now. So now you're getting into really interesting and hard problems. So which the database really should be solving. And there are a lot of complexity in this. Maintainability is hard. Durability, because of this crashing of a cache, means people could see really weird results, okay? And this has actually happened with the risk management app use case I talked about earlier, is they had built it on a cache in front of a relational database. And what happened was the caches will occasionally fail. Failures will happen at some point. You're guaranteed a failure will happen. You're even guaranteed to some extent it'll happen at the worst possible time, right? Like on Thanksgiving Eve or whatever, Black Friday. I mean, it's like I've actually seen this. I would not have believed it otherwise. But the point is, people tend to do things before these events which kind of trigger some weird stuff. But anyway, once it fails, a user ends up who's trading, it gets some information on their mobile device which says, okay, your trade's completed, everything's good. And then they check again. For some reason, okay, this is the other thing people have noticed. If everybody has a mobile device, they somehow want to go check their stock accounts all the time. I mean, nobody ever did that before they had a mobile device in their hand. They check it once a day, maybe once a week. But once a device comes, they're checking it like 100 times a day. Who knows why? But this person sees the wrong thing because the cache failed. Okay? And then he goes like, calls the bank. Hey, I just saw the thing, where is my money? And the bank doesn't want to get calls like this. It's gonna, and of course the data is safe, there's nothing wrong. It's just the perception of putting the cache, it kind of kills a lot of stuff. The consistency is lost. Even though they have durability and consistency in the database, everything is actually fine. It is just that the extra load you put in the system has given you a way to get to a kind of a architecture which exposes certain weird effects to the end user. The cost of this is high, and there's also a data lag because of the cache. So what we ended up doing, over the last 8 years is figure out that if you could build this layer, which can be both a caching layer and a database, again, I'm talking at the context of a system of engagement, which is, I'm not really talking at it yet as a system of record. So this is in the front edge of your, what do you call it, of your enterprise, and it's handling all the requests, it's storing things like fraud information and so on, and computing the risk and fraud, information right here. And this is essentially, if you could just do that, then you would get, first of all, the faster app development is common across many of these databases like Mongo, Redis, and so on, and Cassandra too. Richer data schema is also common, but the real important thing is if you can provide in-memory performance at scale with lower distributed database with a reasonable TCO, and that's kind of what hybrid memory architecture does actually. So what exactly, I'm going to talk about a few things. You can ask me questions, but the point is, there's a VLDB paper, for example, which describes a lot of these technologies, and we'll probably be publishing another one next year because we've added a whole bunch of new things to the database. So what we have here, and these are like basic principles of the database in terms of the system overview. The first one is the distributed hash table algorithm that Aerospike uses is essentially based on the RIPEMD 160 algorithm. We map basically the entire key space into about 4K partitions, and it's a divide and conquer algorithm. And the hashing algorithm is so robust that we can reduce, pretty much eliminate hotspots. We are a shared nothing architecture. Every node is identical. There are no system-wide masters anywhere, so it's very robust. There is a lot of work we did on clustering to make sure that it is very easy to add nodes and remove nodes from the system. It's actually, it's something you can try out also. We have an open source version which you can download, the community edition. Transactions and long-running tasks are prioritized. This is really important. In a long-running system, when you have spikes, you have to realize that when you're taking heavy write loads and heavy read loads at the same time, and there's a data rebalancing going on because a node is coming in or out, a huge percentage of the data could be moving from one node to another node, which means those are long-running transactions. How do you balance those? There's a whole bunch of real-time algorithms we have invented for that. There's also another important thing is in scaling is the ability of the client to be intelligent, because it is very, very important that the client doesn't become a bottleneck and you don't have an extra level of indirection. So I'll talk a little bit about that in a second when I talk about the partition map. Then the other one is XDR. You have a cluster which is tightly coupled, typically within one data center or one availability zone in Amazon, connected across. These are individual clusters connected through some kind of topology to other clusters with subsets of data being replicated in various places to take advantage of to satisfy regional requirements and so on. Sometimes people don't want to move data out of Europe and so on. So you can actually do all of that using these kinds of topologies. So at the highest level, a hybrid memory architecture, it stores all the indexes in DRAM and the data on SSD. Okay. If I'm talking about an in-memory architecture, what that means is everything is stored in memory. It's both indexes and data. This one, indexes in DRAM, data on SSD, we directly read it from flash. And that's kind of the important kind of point here. It provides you predictable performance at a very low TCO and all of the other stuff I'm going to show you. So initially, right, I just wanted to show you there is in-memory, where all the data and indexes are in memory. And then there's hybrid memory, where the data, where the indexes are in DRAM, and the data is directly on flash. You see the read. The read doesn't go to in memory, it just goes directly to the flash, always. Okay? And I'm kind of simplifying it a little bit, but that's essentially true. I mean, there could be something which is in flight to disk, then you read it from memory. You have to read the latest value anyway. The other things that are important is to make hybrid memory efficient, there is direct device access, which means that all these devices are attached in raw mode. That's the best way to do it. It will still work if you don't do that, but this gives you the best performance. We also amortize the writes across large blocks. It's a copy on write system. So every change to a data item is always written to a new place on flash. That's important. And the indexes are in DRAM, so they have to be reconstructed on a complete system crash, for example. It's highly parallelized. I'll talk a little bit about that. And it's a log structured file system, as I mentioned, which is the copy and write. We also, in order to make things fast, we also store the indexes in shared memory. So in a normal rolling upgrade, no matter what the size of the data is, the process can restart within seconds. That's really important.
All right, if the machine reboots, what are you saying we need to recreate the indexes?
From the data on the disks, yes.
So if you had a machine with lots of memory, say terabyte, you can create new indexes in a couple of seconds?
No. Not when the machine reboots, when the process reboots. When it's a rolling upgrade, you're taking down the node. You're not taking down the Linux box.
But if the Linux box rebooted, the time to recreate the indexes would be proportional to the size of the indexes.
In proper size of the data, how long it takes to scan. We keep improving it, but it's not going to be seconds. It'll be hours. If it's a large database, it'll be minutes if it's smaller. But more importantly, that is amortized by the fact that we have a clustered system. So you can have multiple copies. So you never really run into that issue, but there's a reason why we have the fast restart. Now that we have the fast restart, nobody wants to deal with the old one. Even though for years they were deploying fine without that. But that's important. It's a good question. In terms of the idea of putting stuff on SSD actually directly impacts the TCO. That's kind of important to understand, because we have reduced the amount of DRAM that is required. There is no cache, there's no cache misses. There's none of those inconsistency issues I talked about when the caches fail. It's optimized for SSD in this way. So I talked a little bit about the hashing. The hashing is by the RIPE-MD 160 hash function. So we haven't actually invented this. Okay, this is a cryptographic hash which is very robust. You can take any particular set of keys and hash it. It will distribute it really well across partitions. We take about 12 bits. This 160 stands for 160 bits or 20 bytes. We take 12 bits of it and map the partition ID into that. And what you end up doing is you then map the partition IDs to actual nodes. And that becomes the partition map. And this partition map essentially is how the entire distribution algorithm works. It's assigned randomly, and that's really important. So when you have a partition map with 2 columns, it means it's a 2-copy cluster. But you can have more. You can have a 3-column thing, which is a 3-copy cluster, or an n column, which is fully replicated partition, fully replicated namespace. We divide the data in a database by namespaces, and each namespace has its own partition map, depending on what the replication factor is for that namespace. So typically I show a 2-copy one. And then the important thing is the clients are smart enough so that they will share a copy of this partition map. They don't actually participate in how the data is distributed, but they will know where the data is because they share this pieces of the partition map. What that means is with exactly one hop from the client to the node, you know in steady state, you're able to go to the right node to get the data that the client application is interested in. And that's really important for scalability.
Just to clarify, this is an object store, not a relational database.
It's a row store, but it is not a relational database. It's not relational, but everything in Aerospike is a row store because it's not a simplistic key value. The value can be complex, much like Redis. You can have lists, maps of items, lists of items, and so on in terms of the actual columns. And you can have a record with a bunch of columns. We call them bins because it is very difficult to, having been a relational database person myself, if you say column, it means it comes with a fixed schema, it has, alter table. I mean, there's a whole bunch of stuff that comes with it. We don't want to imply somehow that we are relational. Automatic rebalancing is really important, and we use Paxos. Again, there's a lot of these algorithms are in the BLDB paper I mentioned. It's on our website. You can also search for it. It's automatically rebalanced, and that's important. So when a node comes in or goes out, the Paxos algorithm kicks in. First of all, heartbeats kick in, and then the Paxos algorithm kicks in to decide what is the new cluster. And then once the new cluster is decided, the partition map across the nodes is decided, then a whole bunch of partition migrations are scheduled, and then the data will move around in the cluster. And again, while it's doing, there is of course an impact on the amount of resources being used within the cluster, but there's really no impact on the read-write load if you have sized it correctly. And we have a lot of data points and experience in that. The other important thing, right, I talk about, we're going to just stick all the data in SSDs, and then we're not going to put it in memory, only the index is in memory. And the first question comes to mind is, okay, in memory I can easily do 1 million transactions per second. How are you going to do that in SSDs? Well, you're going to have a massively parallel system. And one of the hallmarks of Aerospike is using SSDs and various other techniques we've used in terms of CPU pinning, various other, attaching threads to cores and all that. We scale up a lot. Scale up, everybody does scale up, okay? That's kind of the table stakes, like that. You want to add more nodes, you want the system to cluster, you want to make it work. But can you squeeze every ounce of performance out of the hardware that you have in one node? That's one thing we have spent a lot of time and energy on. So that is one of the reasons why Aerospike's cluster sizes, node sizes will be almost like 10 times smaller than others, okay? In many, many situations. And the automatic distribution of partition, just to illustrate it, right? We not only distribute partitions across nodes, but within nodes, we can distribute the data across SSDs. That's really important, okay? So when you have 5 SSDs per node, you have a 4-node cluster, there is a 20-way distribution. And that's important, because if you have multi-threading at the server level, and then you have multiple disks, you can actually, if each disk can, let's say, each disk can handle 100,000 reads per second, okay? You can do 500,000 reads per second on that node with absolutely no issues. I'm saying 500,000 reads per second while doing a whole bunch of writes per second also, which is large block writes, because you block the writes together. You don't write as often as the application writes. It's similar to what's called group commit in relational databases, but it's not. It's the same idea. It's not the same thing, but same idea. So essentially, that's your parallelism. And then again, we talked about the smart clients already. And fundamentally, we write the code in C. That's really important. No garbage collection. There's no it's a real-time language. It just works very well. We also continually do not just the rebalancing I talked about, defragmentation. We clean up evicted, expired records. All of this happens all the time in this architecture, right? It's really important to understand that we don't have a maintenance window. That is one of the earliest lessons which I had not in Aerospike, but before that in internet companies, is that there are no maintenance windows. I mean, we can pretend that there are, but once it's a global internet companies, there's no maintenance window at all. So eventually, in fact, one interesting thing happened with us is over time, with our first customer, we started doing maintenance during their peak periods. Because they go like, well, that's when I'm alert. You know, the ops person is like, you know, awake in the morning at 9 a.m. and they're not like awake at midnight. So which means we have to make sure the system will actually behave well under high load. And that actually was a good challenge for us, and that went into a lot of the design. A lot of storage optimizations we do. I'm probably have to skip past those, but fundamentally, you know, we do a lot of work in storage. And then again, the code is open source. You can even take a look at it. There are papers written on it. Correctness is really important. I've been saying so much about caches and what they do to you, and we eliminate caches. So in terms of writes, we are what is called, we do synchronous writing within the cluster and asynchronous writing across clusters. That's kind of the most important thing to remember here. So within a cluster, there are multiple nodes with multiple copies of partitions, and we are able to go and synchronously, and then there's a master copy of the partition which will coordinate. The server which has the master copy will coordinate the writes across the multiple copies within the system. Okay? So, and then what you have is the remote cluster is asynchronous. All of this is, I think, pretty much straightforward. The last thing I wanted to mention was we have spent a lot of time in understanding parallelism at the network queue level. You know, the usual kind of things you have to deal with with multi-core, you know, multiple sockets, I mean, CPUs and all that. So we spent a lot of time making sure that a multi-thread, you know, in fact, there's a different philosophy here. One thing I want you to remember is our philosophy is based on multi-threading and figuring out how in one process we can use the CPU and its systems as much as possible. There are other approaches to it, like VoltDB and Redis. They will do single-threaded execution. Okay? Now, we don't believe in that. We think we should solve those problems. Otherwise, you have to go solve it outside anyway, right? So, you know, you run multiple of these processes on one node and so on. We will actually spend we've spent a lot of time in figuring that out. If you kind of get that, that's kind of the basic idea here. What are the benefits of something like this? And this is an actual, screenshot from one of our customers who basically deployed the fraud detection thing. You know, they were running on a relational database and caching algorithm, you know, caching system here. When the cutover happened, you see what happens here is they got to 99.95% from 98.5%. That's actually reducing by 30x the number of lost transactions, if you will. That's fundamentally kind of you know, game changing in a lot of ways, because now they can scale up. That's kind of what they were worried about, is they were going to go 10x more, and you don't want to lose this much. But next thing is low TCO, and this is another example. The TCO difference is purely based on the difference between memory and SSD. The fact that we can actually leverage SSDs mean we can run a smaller amount of server size, you know, cluster sizes than others, right? This was an actual deployment. This was, I think, with Cassandra, with 168 servers, and they were barely getting the latencies that they wanted. And then this is just a sizing sheet, which kind of gives some kind of dollar value. We had to do the first year they couldn't actually, it was all sunk cost the first year, and then they had to upgrade the network. That's the 0.06. After that, as you notice, as they go up, they save more and more money. But here's the thing, the whole sizing went to 44 servers from 168. They actually deployed with 30, that's all they needed. So that's actually pretty good. You know, we have a lot of experience in this kind of stuff. And Aerospike doesn't go, this hybrid memory architecture is suitable for a certain kind of use case. That's the way to put it. It's not like any other particular database is bad or good for this. But people have figured out a way to run it with, you know, DB2 plus Gem5, we replaced that. You know, Oracle plus Terracotta, we replaced that. Cassandra, we replaced that. Coherence, you know. So it's possible. There are use cases for which we are really good fit. Is kind of the message I want to convey here. We don't necessarily run for everything else. I have a couple of slides left. And here's the thing. There are so many other possible solutions here. Okay? Now, Aerospike focuses on the high scale and high speed area, where we're really good at. And why and the question comes, why can't we use any of these other technologies here. Of course you can. People have, you know. And what happens is the cost curve is what kills you. That's it. There's nothing much more to it because you have to take advantage of this and to make it happen. Okay. So I've kind of mostly focused on the current product as it's deployed right now. This one slide, I'm departing from that. We just announced Aerospike 4.0. What we have realized is, while there are lots and lots of databases that are highly consistent, strongly consistent I would say, they are not high performance. So we've spent a lot of time, we spent about 2 years coming up to this release, where we're basically releasing a strongly consistent Aerospike, which preserves pretty much most of the high performance that we have. The basic invariants we will support there are linearizability and session consistency. We are a single record database, so linearizability is the highest level we can support. Serializability applies for multiple record transactions. So that's, I'll close with that. If there are any questions, we probably have a couple of minutes to answer. And sorry, we started late because we just couldn't figure out the Mac thing. Kept crashing. Thank you.